Okay. All right. So we're discussing fusion propulsion, but really more than that, we're discussing uh, the Promethean action, the leadership action that's required to take civilization to higher levels. This is a statue that was made by a Czech-American sculptor. He made about 50 copies of it, but it sort of represents the idea that we have to promote and we have to create the conditions for people to develop their creativity and create the technologies and the ideas that are necessary to move to higher levels. So we've had all kinds of people that they didn't always agree with each other. Oftentimes they were opponents. They were involved in various fights with one another. There are some examples. There are also people who, you might not 100% agree with everything that they believed or stood for, whatever. But one very important person that we're going to highlight tonight is Lyndon LaRouche. In 1988, he made a proposal that the United States government make the decision that we should build a city on Mars within 40 years. And of course, at the time, this was considered to be a crackpot idea. And he received lots of flack from it. But the idea was an idea that couldn't be stopped, and it permeated all around the world. And so by 2017, a lot of what LaRouche had proposed way back in '88 became national policy, where President Trump signed the Space Policy Directive 1, which said that we're going to go to the moon to create a permanent basis of human operations on the moon, and we're going to send people to Mars. He didn't go so far as to say we're going to build a city on Mars, but he adopted quite a bit of LaRouche's proposal in the Artemis project, which he began. And we'll talk a little bit more about that later. But Artemis, this is a project which we've begun, which we don't have all the solutions for making a permanent base of operations on the moon yet. There are lots of problems. But more important than the particular problems once you're there, the question of getting to the moon and getting to Mars involves solving a bunch of different questions which you don't have to deal with here on Earth. And it requires a different strategy, different concept of the ordering of space, because space has harmonic ordering principles, that there are gravity fields, there's radiation, solar wind, all kinds of particles, and we have to find force-free pathways across vast distances. You're not going to find any straight lines in space. Even light doesn't travel in a straight line. A straight line is a mental construct that doesn't really reflect reality. And to the extent that we have Euclidean geometry in our minds, it pollutes our ability to make the discoveries and to accomplish the tasks which need to be accomplished to spread civilization to the moon and Mars. So, for example, here is the pathway taken by Perseverance in its flight to Mars. It took about 7 months, and that's pretty typical for sending a probe to Mars. But if you were to send people on a 7th-month journey through space without any propulsion, you have the problem that when you arrive at Mars, your bone density and your muscle mass will have decreased quite a bit, so that you won't have the same capabilities you had when you left Earth. So yesterday, Elon Musk gave a presentation in Starbase, Texas, which used to be called Boca Chica, Texas, to his SpaceX team, and he discussed the idea of getting a million tons of hardware and various kinds of equipment to Mars over an 8-year period. And I'll discuss a little bit more about that later, but that's one thing for equipment. It's okay for equipment to take 7 months to reach Mars, but it's not the best thing for people. So what are we going to do about this? This is another way of looking at the situation that you face when you're talking about going to the moon or Mars. This is a gravity well graph, which demonstrates the relative energy required to go to the space station versus geostationary orbit or the moon. Once you're out in geostationary orbit, or once you're at the or near the moon, it's very easy to go to Mars and go anywhere else in the solar system. But there's a huge amount of energy which has to be expended to get there. So where are we going to get that energy? On the moon itself provides a lot of resources that we can use to build some of the tonnage that we send to Mars, because there are all kinds of metals up there in high densities. We've got water up there. We don't know exactly how much or where exactly, but there is water up there, which is very important for hydrogen and oxygen, both for fuel and for breathing, for human settlements and other such things. So anyway, so we're going to discuss, as I said at the very beginning, rocket propulsion. And rocket propulsion goes way back to the development of gunpowder in China, which happened way before 142 AD. That's the first reference that we've seen of it in written materials. And you have basic principle that if you have an action in one direction, you're going to get a reaction in the opposite direction. That's a very simple principle. You can demonstrate it to yourself. Generally, we use it for rockets going into space. We usually use chemical rockets, which consist of an oxidizer and a fuel. And this is a diagram of the A4. This is the first rocket that actually entered space, went outside the atmosphere and entered space, the A4, which later became known in the military version as the V2, under the design of Wernher von Braun. But anyway, as I was saying yesterday, there was this discussion by Elon Musk, and he discussed what they're doing at SpaceX, which is very important, but it has limitations because, well, we'll discuss that in a minute, but chemical rockets, the good thing about chemical rockets is that they have a lot of thrust. They're good for taking off from the Earth. They're good for retrograde action, it's essentially acting like brakes, things of that sort. But they have limitations. But anyway, what he was discussing yesterday is very interesting. He said this year, SpaceX is going to be putting 90% of the mass that's put into orbit will be put into orbit by SpaceX Falcon 9 rockets. 6% will be accomplished by China and 4% by the rest of the world. The Super Heavy booster, which launches the Starship, will become reusable this year. And each Starship, he intends to be able to put 200 tons into Earth orbit. So if he's producing 1,000 Starships per year, you can get 1 million tons to Mars in an 8-year period of time, four Mars cycles, approximately every 2 years, or 22 months, something like that. Approximately every 2 years, the Earth and Mars are in the proper orientation to make the simplest transition to Mars. So anyway, that's pretty good. But the problem with chemical rockets is that it's like driving your car, getting in your car in the morning, revving up your car, going as fast as you can, and then turning off the motor after 2 minutes, and then trying to glide into town to go to work. and then maybe turn your engine back on when you're going to park your car. But anyway, it'd be much better if we had continuous power over the long term, instead of having to fire everything we've got, run it till it's almost empty, and then coast. So there are a bunch of different technologies for propulsion besides chemical rockets. And there's different ways that you can look at the characteristics. Like, for example, in this chart, we're examining the specific impulse. Specific impulse is the sort of the miles per gallon for rockets. Okay, let's put it that way. The simplest expression. It tells you basically how long you can use a kilogram of fuel to move a specific mass. So anyway, so you see here that so the Raptor engine, which is what powers the Starship, is just under 400 ISPs. And you look down to nuclear thermal rockets. A nuclear thermal rocket, which we'll discuss further down, is a rocket that uses a nuclear reaction to heat up a gas, basically, oftentimes hydrogen or helium or some other gas to a very high temperature. And by using those types of rockets, you can get about a little better than double what you can get from a chemical engine. But then we have what's called electric propulsion, which gets way higher propulsion per unit mass, let's put it that way, of fuel. And we're going to discuss those briefly here. But the basic idea with electric propulsion is that you are using magnets, electromagnets, to accelerate ions. Ions are atoms whose charge has been changed from neutral to positive by stripping an electron off the outer shell of the atom. So anyway, so by giving the atom an electrical charge, a magnetic charge, the atom can be controlled by magnetic fields. So if you have magnetic fields accelerating these atoms out to the back of your rocket, you create a thrust. Now, the thing is that, like, for example, this Hall thruster that we're looking at here, it would have about the power of a piece of paper sitting on your hand, pushing down on your hand. So it's not very much, but if you're able to do that for days and months and years, it has a great effect. And these are on almost all satellites these days for purposes of station keeping, and they will be the main means for moving the lunar gateway, which NASA is building as a stepping off point for Artemis missions to the moon, and also for missions to Mars, which will be out near lunar orbit. So this is going to have electric propulsion. So these are very efficient ways to use your kilograms of fuel out in deep space, so that you have the ability to have power over long periods of time. Now, this is an adaptation of a similar process. It's called a Vasimir engine variable specific impulse magnetoplasma rocket, which is being developed in Houston here by Ad Astra. This particular design not only uses the electromagnets, but also uses radio waves to heat up plasma. And because of the addition of the radio waves, this allows this rocket engine to have a variable thrust. So it's not just on or off like those other electric propulsion systems, but it's sort of like having a jet engine with an afterburner. So it's a little bit more powerful than most electric propulsion systems. But anyway, if we really want to go beyond the solar system and we want to go to Mars and send people there and have a chance of people getting there within say, a few weeks instead of 7 or 8 months, we really need to have fusion power. And here we're looking at these rocket types from the standpoint of their exhaust velocities. You see the comparison there between fission powered rockets, fusion powered rockets, and antimatter rockets, which are way out there in the distance. But anyway, there are things that we have to think about, because those are the kinds of technologies which will allow us to go beyond Mars. And for example, to go out to, the nearest star is Alpha Centauri, and that's about 4.3 light years away. So if you were a beam of light, it would take you 4.3 years to get to Alpha Centauri. So if you really want to go there, you got to be going some significant fraction of the speed of light, and chemical rockets are not going to do it. And this is another comparison. My colleague Kevin here will go over this a little bit more when I finish going through this, but this is a comparison between chemical rocket exhaust velocities, nuclear thermal rockets, the nuclear rockets that are powered by the heat of the nuclear reactor, and then thermonuclear fusion rockets, and also, again, matter-antimatter reactions. But for example, the fusion rocket, which we're going to discuss a little more later, that's being jointly developed by Princeton Satellite Systems, which is an offshoot of the Princeton Plasma Physics Laboratory, and also Pulsar Fusion, which is a UK-based company. They're jointly working on a fusion reactor-based rocket, and they're trying to get exhaust velocities 1,000 times those of the electric propulsion systems. So this is a schematic showing the basic configuration of a liquid rocket engine versus a fission or fusion reactor design, which is using the heat generated by fission or by fusion to heat up a gas, which is one of the ways that you can build a fusion rocket, and one of the ways that you can use fission to run a rocket as well. It's not the only one, but it's one of them. So this is a schematic of the first American nuclear thermal rocket from the 1960s. And it was actually tested, and it worked, and it was running at about 900 seconds, or about double what the Saturn V engines or even the Raptor engines of today get. And right now, NASA and the Department of Energy, they've got 3 ongoing contracts for the development of nuclear thermal rocket designs. Thermal rocket designs that, because they use the heat from the nuclear reactor to heat up a gas. So as I say there, the specific impulse of those engines is about twice of what you get with most chemical reactors. And of course, just in general, fusion energy power has got 1,000,000 times the energy density of a typical fossil fuel. This is from our previous discussion, but I'm just showing it here so that you get that idea again. So the first idea is about using fusion for propulsion, centered around the hydrogen bomb. People thought, well, we know how to make hydrogen bombs. We know about fusion. What happens if you drop hydrogen bombs periodically out the back of your spaceship? And that resulted in Project Orion H-bomb propulsion system, and that is something which probably would work, but it's sort of brute force. it's along the lines of the inertial confinement fusion project that Lawrence Livermore National Laboratory has successfully used to produce more energy out than energy in on a pellet hit by an array of lasers. That it does work, but bombs and inertial confinement are a little bit along the lines of brute force methodologies. And this is an inertial confinement laser fusion concept for a rocket. This is a recent design. But anyway, the thing that LaRouche talked about, and other people like Professor Dan Wells, who promoted taking other approaches to fusion energy for propulsion and for electrical power generation, things of that sort, is to use the self-organizing principles which already exist in plasma and electrodynamic systems. So I'm showing you here a little bit of a curveball physics here, that you apply a rotation to the ball and you're transforming the physics of the motion. If you're a smoker, you may have noticed that you can create these smoke rings. A smoke ring is characterized by the smoke curling around itself in a ring. There's a self-organizing process which tends to confine the smoke on its own without any external intervention. So if you can use these kinds of self-organizing principles to control the plasma, you can get much more effective output per input in your design. And so this is called a field reversed configuration. You can call it a smoke ring configuration, but technically it's called a field reversed configuration because the field is reversed backward upon itself and actually acts to constrict the plasma within the ring. And this is the configuration that's used in a number of fusion reactor systems, especially, for example, the Helion company's approach, which is supposed to be producing electricity this year and is probably going to be the first fusion company to actually build machines that produce electricity for useful work. But it's also the design that's being used by what I said before, the combination of Princeton Satellite Systems and the company from the UK that are working on this type of a design for a rocket engine. So you have the Princeton Satellite Systems and Pulsar Fusion, they're working together on this configuration. There's another company working on a fusion rocket called Helicity Space, and they have a proprietary system which I don't understand that well myself, and there's very little information publicly available about it, so I'll just say it's proprietary. And then there's Rocket Star, which is instead of using helium-3, they use boron, very much like another fusion company, TAE, which has a boron fusion concept. But as we discussed 2 weeks ago, there are 40 or 50 companies that are working on fusion, but these are companies that are working on fusion rocket systems. And I just threw this up here because this just shows you some of the companies which received contracts last year for fusion power plant development designs from the Department of Energy. And these are just a few of the many companies that are working in this area. And this is a fusion reactor design rocket, which was built as part of a NASA contract roughly 10 years ago by a company called MSNW, which doesn't exist anymore. But the problem we have in making these slideshows is that everybody's got their proprietary rights over their technologies, and we can't just show you the latest and greatest designs and equipment without going through the process of getting permission. So this is a 10-year-old design, but you'll have to settle for that. But the designs for fusion rockets, which are ongoing at the moment, are you can think of them as elongated extrapolations of this design. So here is a picture of a reversed field configuration pulse at the Princeton Plasma Physics Laboratory, which is where the Princeton satellite systems ideas are tested. So one other thing which we discussed with LaRouche was the idea that if you could have enough power that you could accelerate at 1G toward Mars and then turn your rocket around and decelerate at 1G, that you could get to Mars within several days or a week, say something like that. So go ahead. Were you going to say something, Kevin?
Yeah, it is about 2 days.
Yeah.
If you're going at roughly where the orbit of Mars and Earth are near closest approach, you're basically just going orthogonal to those two orbit paths, right? You don't have to go on an arc like we saw with Perseverance.
Well,
you just
still
go
be an arc, but it
one
would be
orbit to the next, because you're going so fast, you can kind of neglect orbital mechanics. And yeah, if you go at 1G half the way and then decelerate 1G the other half of the way, you'll arrive at rest in 2 days. That's very true.
So this is from a blog post from Stephanie Thomas, who's the vice president at Princeton Satellite Systems, because someone had written to her about that. So she's building a fusion plant, but she said, in order to accelerate 100,000 pounds at 1G and arrive at Mars in around 2 days, you'd need over 2.8 terawatts of power. And that's about equal to the total power output of the entire Earth. But anyway, they're estimating that their rocket, which they call the direct fusion drive, would produce about 1 megawatt per ton, and that they could reduce the trip to Mars to 90 days from 7, 8, 9 months. That's what they're talking about. We're not in the position yet of building rockets that can get us to Mars in a few days, but we can radically reduce the time that people have to go through the deep space problems that are associated with radiation and also weightlessness, because you can have continuous power. Continuous power is a big shift in moving around in the solar system. Okay, so we've been talking about some of these things, but we have to talk about the political situation a little bit here too, because we have all these companies, we have people who are trying to do the kinds of things that Edison and the Wright brothers and other people have tried to do in the past, but they're hindered left and right by the predatory imperial speculative process that basically tries to suppress and destroy any kind of progress. They push the green agenda, the cult of global warming, which they changed the name of because people didn't notice that they were getting warmer. similar sorts of things. We have to destroy that, and we have to protect American creativity in research and production. And one of the most important things is that we have to have national bank credit. This is the second bank of the United States that was shut down by Andy Jackson. And here is the Federal Reserve, which was set up in 1913. But, building-wise, they look a little bit similar. They have some similarity in design of the building, but their objectives are totally different. The objective of the Federal Reserve is not to create credit for the production of anything. They exist in order to manipulate the price of money and price of various types of things, because the oligarchical imperial system of the British Empire is based on manipulation of conflict and prices and basically wiping out competitors by driving them into bankruptcy. So anyway, so along with the Artemis project, we have to implement finally the North American Water and Power Alliance project, which is a 30 to 50-year project, which means that you're going to create a market for steel, for concrete, for skilled civil engineers, and everything that's involved for a 30 to 50-year period, because you have to have such a market to justify and allow for investment in those areas of the economy that will create the basis for the productive society that we need to have. So this is the kind of thing, along with the colonization of the moon and Mars, which helps to organize society, the whole of society, around production and creating a better future for all. So, pulling the people, ideas, and resources of the country together via the grand colonization of the moon and Mars will bring the productive power of the country to unprecedented levels, lift the spirit and outlook of the citizenry, restore a bright future to the young, and bring the entire world economy into this process, thereby extending these benefits to all of mankind. And that is why we're talking about what we're talking about. We're not just a bunch of nerds talking about nerd things. So anyway, Kevin probably has some more he wants to say about some of these slides, because he introduced many of these slides. He probably has more to say about them before we open for questions.
Yeah, since it's about 7:30, and we've got a little bit of time here, so why don't we take a few moments and maybe go into a little bit more of the physics on the difference between today's rocket engines, the chemical engines, and nuclear and fusion engines. So, Mike, if you could find, I think it was page 26, maybe we'll just spend 5 minutes on going through that a little bit. There it is.
This one?
Nope.
No, the previous one. This one.
The one right below, go down, I think 1, 2, 3 to 27, it looks like. Next one.
One more.
One more.
This one. Yeah, okay.
There you go. All right.
You think you can blow it up bigger, Mike?
Oh, yeah, that would be good if you can blow it up.
Oh, yeah. Did I forget to do that?
Yeah, we should have told it to go to
Oh, yeah, I forgot to do
presentation mode.
Yeah. Okay, all right.
All right. So on the left is, we basically got a liquid rocket engine. There are also what are called solid rocket engines, which we kind of use we do use for our ICBMs and so forth, because they have good storage life. But in any event, what's going on is you have a fuel and an oxidizer. The most energetic fuel is hydrogen. And so they'll put liquid hydrogen in, say, the red tank there on the left, and then liquid oxygen in the blue tank. Elon Musk chose methane for his fuel. Part of that thinking was because if he goes to Mars, and Mars has an atmosphere of carbon dioxide, he can create methane on Mars and then be able to produce fuel and come back to the Earth. So that was part of his decision-making in choosing methane. And methane is a good energetic fuel. If you burn hydrogen and oxygen, of course, your exhaust will be simply water vapor. If you burn methane and oxygen, you'll get carbon dioxide and water as your exhaust. But what basically is going on is you have some pumps, and they pump both of the fuel and oxidizer into what we call a combustion chamber, and they burn. And for example, actually methane and oxygen burn quite hot in about 3,500 Kelvin. And to put that into perspective, stainless steel melts at a lower temperature than that, 1800 Kelvin. So these rocket engines are a marvel of engineering because you've got to be cooling the combustion chamber and also the nozzle to keep them from melting. In fact, they use usually an ablative material out in the nozzle to help with that. And you also get a lot of heating in the throat because the exhaust goes through what's called a converging diverging nozzle there. But why do we have to combust well, let's back up a little minute. Most of you have watered your lawn and you have a hose, and if you hold the hose, you're going to feel a little reaction force when the water is coming out of the hose. And some of these hoses, you can have a big stream and then more of a light spray stream. And you might notice that as you change the type of spray you're getting, the reaction force on your hand changes a little bit. And so what's going on is there's really two knobs or two parameters you can adjust to get a given thrust from a rocket engine. And one of these is the mass flow rate, which is the amount of mass or substance coming out of that nozzle per unit time. And then the other parameter you can play with is the actual speed of that mass. So just to make this a little more clear, think of the mass being some rocks. And suppose I've got two rocks and they're each maybe a kilogram. And I throw one rock out of the nozzle every second. So that means I'm getting one rock a second. Since each rock weighs a kilogram, the mass flow rate is 1 kilogram per second. I can throw the rocks out faster at a higher rate. I can do 2 rocks a second or 3 rocks a second. But notice I'm not telling you about what's the speed of those rocks. I'm just throwing them out of the nozzle. So that's another free parameter, the speed of the rock. And if I throw the rocks out faster and at the same rate of rocks going out, I'll get more thrust. And so you'll see that little equation. If you took high school algebra, you've got that the thrust is simply the product of the mass flow rate and this exhaust velocity. So I can do two things. I can put out a lot of mass per unit time at a given speed of those molecules or that exhaust, or I can have a reduced mass flow rate and increase the speed of those molecules. And both ways I can get the same thrust. So but the problem with chemical engines is to get the mass flow rate, I've got to carry out the mass on board and I've got to burn all that. And actually, my mass flow rate is simply all the mass I'm carrying on board as propellant divided by the time it takes to burn it all. That's that mass flow rate. And I'm limited by the exhaust velocity because that's a function of the temperature I can achieve. We talked about that with fusion 2 weeks ago. The kinetic energy of gas molecules is really a function of their temperature. And so the speed goes kind of as the square root of the temperature of the gas. And so I'm limited there with combustion. I can't combust any chemical materials much higher than 3,500 Kelvin. So to get more thrust, I've just got to play around with that mass flow rate. And that means I got to increase my thrust and go faster, I've got to carry more fuel. And so you can see there's a point of diminishing returns there. And that is kind of why we've got to move to a new technology beyond chemical rocket engines to go to Mars much faster, and then eventually even to go to nearby stars much faster. So, and that new technology is there on the right, because what's different there when we look at a fission or fusion nuclear rocket? You'll notice there's no combustion process. So here, the heat is not coming from chemical combustion. So I'm not limited to 3,500 Kelvin anymore. The heat here is coming from either fission or fusion. And the fuel here is the hydrogen. We're not combusting the hydrogen. We're simply changing it from a liquid to a vapor. And if we heat it enough, we can even ionize it. And so I can get much higher temperatures with fission and fusion. That means I can get much higher exit speeds, that exhaust velocity. And in fact, I can make those exhaust velocities so high that I can make that mass flow rate very low, which means I don't have to carry near as much liquid hydrogen or fuel mass to get a lot of thrust and to get a lot of speed. So that is why, hopefully I made that clear, but that is why we're moving to these new advanced fusion and fission rocket engines. And let's go, I think one of those charts, Mike, where we showed the comparison, let's just point out the big difference in, yeah. So notice on the far right column, that's labeled the spacecraft mass to reach Mars in 2 weeks. Well, to do that, as we talked about, you have to reach a speed of 80 kilometers per second. That's virtually impossible to do with a chemical engine. I showed you how big a chemical engine would be. Look at that. You're carrying, I don't know, 263, I think that's trillion, kilograms of hydrogen and oxygen to do that. And it's really not a feasible rocket engine. If you go to these nuclear engines where you heat hydrogen with nuclear or fission, the mass of the spacecraft, and basically we're talking about the mass of that propellant you have to carry, gets smaller. And notice, why is it getting smaller as we go down the column? Well, it's because the exhaust velocity is getting higher. And that's that trade-off I just showed you on the other page. So as the exhaust velocity gets high, the amount of propellant mass I have to carry goes way down. And when I get to the direct fission and fusion concepts, where basically we've got a fusion reactor and we've got charged particles or ions, and we're containing them in a magnetic bottle. And that's how we keep things from melting, because they're in a magnetic bottle. But here I can reach exhaust velocities that are fractions of the speed of light. And notice that basically the amount of propellant I have to carry is negligible compared to what we call the dry mass or payload mass of my rocket. In all of these cases, my payload mass is 5,000 kilograms, and all those weights in the column are a little bit bigger, and that extra weight is the propellant I'm carrying. When I get to the very best rocket we can think of today, it's a antimatter rocket. Notice that the exhaust velocities are extremely high, and I'm carrying only 1 kilogram of fuel to reach a speed of 80 kilometers per second for a payload of 5,000 kilograms. So that's where we have to go. And if we reach if we can develop those rocket engines in the bottom of this chart, we will be on our way to not only going to Mars and maybe the moons out in Jupiter and Saturn, but then also visiting the nearest star, which is Alpha Centauri. And that'll be the first step to extending humanity beyond our solar system. So I think that's probably good to go to questions then, Mike, unless you want to say more.
Okay, yes, we can open it up for questions.